Welcome back to the third session of the day two of our FDP. Like I said, the third session is also planned as hands-on with a virtual demo on IdeaMaker 3D printing software. Now, to handle this session, we all have another technical expert from Insta 3D Technologies, Coimbatore. Let us welcome Mr. Joseph Matthew to lead the session. Before we proceed to the session, I would like to introduce Mr. Joseph Matthew before you. Mr. Joseph Matthew is currently the managing director, one of the managing directors of Insta 3D Technologies, Coimbatore. He completed his Master of Engineering in the discipline Advanced Manufacturing Technology. Earlier, he worked as assistant professor at the Karpagam College of Engineering. He has also worked with the projects by Ford India Private Limited. Currently, he is pursuing his PhD in 3D printing technology. With this short introduction, I would like to welcome Mr. Joseph Alex to handle the next session, session 3 of day 2. Over to you, sir.
Thank you, sir. I would like to thank Dr. Lijo Paul and Mr. Pradeep for this wonderful opportunity, arranging a session on IDEAMAKER, virtual demo on IDEAMAKER software. So hope all had your lunch and you'll be dizzy right now. I know that. I'll try to finish as soon as possible and explain you all the parameters and the slicing parameters and the software in short, and we'll have a discussion at the end of the session, so you can ask me your queries, and I think Mr. Mohammed Bashir has already taught you Cura in the morning session. So this IdeaMaker software is more or less similar to Cura, where every parameter is the same, just that the interface differs from Cura. So let's start the presentation now. So I'm Joseph Matthew, one of the managing directors of Insta 3D Technologies LLP, Coimbatore. So to start with, a manufacturing process is divided into typically 3 types right now: additive, subtractive, and hybrid. And it's generally divided into additive and subtractive manufacturing. So in subtractive manufacturing method, I'd like to go across the basic concepts so that there will be a connection between each and every concept. So you can very well understand what are the parameters which is involved with additive manufacturing. So in case of subtractive manufacturing method, there is a tool which removes material from the raw material. So you can get the final output or the final product out of the subtractive manufacturing machine. So in this subtractive manufacturing machine, there are many processes like CNC, milling, drilling, EDM, grinding. Everything comes under subtractive manufacturing process. And certain process parameters which we tend to control is the feed, speed, tool orientation, cut direction. These are very much well known to you since we have worked with lathe machines or even CNC machines in colleges. So you'd have worked with these parameters: feed, speed, tool orientation, cut direction, coolant, depth of cut, tool geometry. All these are very much familiar to you. So whereas in additive manufacturing, you know what is additive manufacturing and what are the technologies available. I've seen your brochure. So there was a session for different additive manufacturing technologies. I would like to brush up few concepts from the technologies available also. So in additive manufacturing process, the design data which is generated from a design software, it is converted into slices, or it is used to build a component in layers by depositing material one above the other. It's like building building. It's like building a building. So in additive manufacturing process. As you see in the image, this is the upper one is the subtractive manufacturing process, where the product is machined and the material is removed from the raw material and the final product is arrived. Whereas the scrap and waste in this subtractive manufacturing process is very high. Whereas in additive manufacturing process, what's the required amount of raw material for a product, only that is required to make the final outcome. So you're using the exact, more or less exact amount of material, raw material, and the 3D printer deposits is by layer deposition, and the final product is obtained. In this case, the scrap and waste is very less. This is a basic difference between the subtractive manufacturing process and the additive manufacturing process. So in all the cases, like, both are beneficial in different ways. So it's our necessity or our application which is used to choose the process of additive or subtractive manufacturing process. So this additive manufacturing, one of the additive manufacturing process is rapid prototyping, and this is nothing but the 3D printing technology. It's the official term for 3D printing. So it's the automatic construction of physical objects using additive manufacturing technology. There are other terms as well for rapid prototyping, which are solid freeform fabrication, automated freeform fabrication, 3D printing, solid imaging, layer-based manufacturing. There are several other terms which are a substitute for rapid prototyping method. So generally, everyone would say 3D printing technology. The exact term for this is rapid prototyping. So under rapid prototyping, 3D printing is a technology. That's the exact definition. And there are different, as you know, there are different technologies available in 3D printing. So these different types of 3D printing is classified based on different building mechanisms, different price points, different materials used, and different applications. So these are the general classification of a 3D printing technology. The first one is FDM, which is a material extrusion method. The second one is SLA or DLP, which uses resin vat polymerization method. Third one is SLS, which is called selective laser sintering, which uses powder as raw material. Preferably nylon material is used in SLS machine. And the next one is material jetting DOD. It jets the material through multiple nozzles. So next, fifth one is the binder jetting method, and the last one is metal printing. So these are the general classification of 3D printing technologies. So first, let's take a look on the FDM process. Today, I'm going to teach you how IDEAMAKER software works. So it's better to know how a FDM process takes place, and so you can interrelate the components used or the process parameters along with the components which are used in FDM process. So in FDM process, you would have three axes: X, Y, and Z. So it's a 3D printer, so obviously you will have three axes: X and Y, and the height is Z. So these three axes is controlled by motors. Preferably stepper motors or servo motors are used to control the motion of the FDM 3D printer. So in this X, Y, and Z axis is available, and this XY motion, in the XY motion, there is a extruder head through which the raw material flows through. So the raw material used here is a thermoplastic raw material. So in FDM process, the raw material uses thermoplastic. So you can use PLA, ABS, PC, nylon, even PLA carbon fiber, and other composite materials are also nowadays available for a FDM process machine. So in this case, in the diagram shown here, there are two materials which are used. One is the build material and the other one is the support material. So once the machine starts to print the G code which is taken out from the software, The spool gives the material to the extrusion nozzle, where the printer filament is heated in a heated cartridge and flows out through the nozzle. So this is the process by which every layer is getting deposited one over the other, and this support material is used to support the overhanging parts, build material. So in this case, you will see 0 degree angle in a build material in the product. So this light blue color represents your supports, which can be broken away, or we can use water soluble support structures to get it from the original part. So in case of FDM technology, these are the basic parameters which can be varied. One is the layer height, which is the thickness of each layer that is being deposited onto the platform. And the second one is infill ratio, the amount of material inside the 3D printed component. And shell, which is nothing but it's the outer perimeter, number of outer perimeters that is enclosed or the enclosed in the cross section of the product. For each layer, there will be shells which is produced, and inside the infill ratio is infill will be coming. So I can show you the previews that is happening in the software. And you can also change the infill patterns that will also be dealt in the next few slides. So as we are talking about FDM machine, there are few problems which is happening in an FDM 3D printer. The first one is warping effect and the layer addition. So this warping effect is like when the 3D printed component absorbs moisture from the environment of 3D printing, the material tends to cool in an uneven manner, so it can start bending in the upward direction. Like once the first layer is formed, and then the second layer starts forming above the first layer. So the uneven cooling or the uneven temperature that is happening in the environment can cause internal stresses, and it forces the first layer to bend upwards. The second layer pulls the first layer to bend upward. So there is an effect called warping which can take place. And next is the layer adhesion issue. So when we are using ABS or other kind of engineered materials, there is a problem of layer adhesion happening. And in this, the layers do not interfere with one another. Like there will be a line or intermediate warping can also take place in the 3D printed process. So we have discussed about FDM technology. What is FDM technology? So in this, we have seen what are the parameters available, important parameters available, and how how a FDM 3D printer works in such a manner, like what are the factors available and what are the parts available in a FDM 3D printer. So using this, we can relate to the 3D printer software. So before going there, I'll just go through the general classification of 3D printing technologies. This is the DLP or SLA technique. SLA is called stereolithographic apparatus. So this uses resin as raw material, whereas FDM uses thermoplastic filaments as raw material. It's a solid-based extrusion method in FDM, whereas it's a liquid-based raw material which is used in SLA and DLP technique. So in this, the difference is only the light source. In SLA technique, the laser source is used as the light source, where it cures the resin. And in DLP technique, the projector cures the resin in order to make the 3D printed component. So this is a new form of 3D printer, a hybrid SLA printer, SLA LCD 3D printer. This uses a LCD screen similar to your mobile phones, where nowadays we can also use mobile phones to 3D print components, where the size of the component will be minimal because the mobile phones are very small. So this SLA LCD printer nowadays there are we can use our mobile phones to 3D print components using this SLA LCD technique. Here, the LED screen or LCD screen is used to cure the resin. So in this SLA technique, the printer parameters are fixed by the manufacturer, and we cannot change much of the parameters. The main parameters which can be changed is the layer height, support details, build size, and similar to FDM, there are problems like curling, layer adhesion in SLA technique as well. So when we compare between FDM and SLA technique, the difference is the SLA technique. In the SLA technique, the 3D printed component is very it has a smooth surface finish, whereas in FDM technique it has a rough surface finish. And in terms of accuracy, SLA is more accurate than the FDM technique, but due to the cost or running cost, mostly we will be preferring FDM over SLA for a normal startup or a student version 3D printers. So we will go with the SLA machine if we have a lot of research or we have a multi-versatile versatile 3D printing requirement. So this is the SLS technique where powder bed is being used in order to form the component. This powder is the nylon powder, polyamide powder. So we can they'll be using laser to sinter the component, final component. Layer by layer, it will be developed. So next technique is the material jetting technique, where the material gets jetted through number of nozzles, and you can combine materials in this material jetting 3D printing technique. One of the examples of material jetting 3D printing is polyjet 3D printing, where you can combine two materials in order to vary the hardness of the component. So if we need a shore hardness of D40, we can do it by mixing both the materials. You will have a flexible one, and the other one hard material is available. You can vary the proportions of both the materials so that you can get the amount of hardness. You can vary the hardness in this material jetting 3D printing technique. And it also uses a UV light source in order to cure the 3D printed layer. So these are some of the examples of a material jetted 3D printed part. Here, the white represents the hard component, and the black one is the soft component, which is flexible or of less hardness. So you can achieve both these finishes in a material jetting technique. So one is glossy finish and the other one is matte finish. The difference is in glossy finish, we will be using minimal amount of support structures, and in matte finish, the whole component will be immersed inside the support structure. So every part will look matte in nature, whereas in glossy technique, the overhanging structures alone, you will get the matte finished component. Rest of the things, it will be glossy in nature. Next is the binder jetting technology. This is similar to the SLS technique. Here, instead of lasers used in SLS technique, this uses binders, which combines or merges two layers to one. So in this full color printing and high volume printing is possible in a binder jetting technology. And you can also use it to produce sand casting cores and molds. And these are physically, like mechanically less in strength. So you can use other techniques like infiltration or sintering techniques in order to improve or enhance the mechanical characteristics. So the last one is the metal printing. Small batch manufacturing. It is used in small batch manufacturing process. It's similar to the SLS technique, whereas it uses metal powders and a high power laser in order to sinter the metal printed component. So we have seen the different 3D printing technologies now. I've just brushed up all the 3D printing technologies where you have seen the differences in the working principle. So today we are going to concentrate only on the fused filament fabrication technique or the fused deposition modeling technique, FDM or triple F technology. So, as I said, in triple F or FDM technology, the current when we see the current research papers, you'll come across these terms: PLA, ABS, ABS, CF. CF is carbon fiber. Then PLA, CF. PLA combined with carbon fiber, PETG, ASA, acrylic-like material, nylon, and PC. So these are the basic filaments that is involved in a FDM or triple F technology. The first technology which I explained with the working principle. So in this, all these are thermoplastic materials. So these thermoplastic materials can be reused even after 3D printing. So this is one of the best advantage of using triple F technology. Whereas when we use SLA techniques, there are few resins which cannot be reused. It obviously goes into the waste after using the component. Whereas in triple F technology, the plastic used can be reused, can be remelted and form into filaments. So these are the different process parameters available in FDM or triple F technology. So we can go through one by one. The first one is the layer thickness, shell overlap, infill density, infill pattern type, infill angle. Like the basic classification is layer thickness, shell, infill, and temperature, speed, the belt orientation, nozzle diameter. These are the basic classification, and within that you'll get to know shell thickness, shell overlap, infill density, everything. So the next characteristics are dimensional accuracy, surface roughness, mechanical properties like tensile, compression, flexural, yield strength, impact, elastic, hardness. Everything can be analyzed in this 3D printing technique by varying the process parameters. And you can also analyze the build time, lattice structure, and the build volume for each of the combinations. So these are the process parameters involved in a FDM technique, and these are the characteristics that can be studied by varying these process parameters in FDM technology. So let's come to slicing. So what we do is, once a 3D design or a 3D model is being generated from a design software, we will be converting it into a common file which is called STL file. It's called Standard Tessellation Language, STL. The file you can see in every 3D design software. Like if you are using SolidWorks, just after designing your component, you will be saving it as STL format. So it is a mesh-like file where we can where the 3D printing software accepts only STL, OBJ, or WRML files. So these are the general categories which is being inputted into the slicing software. So this slicing software is an interface which is used to convert the digital 3D models into printing instructions. That is called G codes, into G codes. It will convert the 3D models into G codes, and the G code is in turn given to the 3D printer to build an object. So this is the use of a slicing software. So the 3D printed, the 3D designed model is being converted into STL file, and the STL file is inputted into the slicing software, where the design file is converted into a G code file. The G code file is in turn given to the 3D printer, and the 3D printer does the job, does the manufacturing job at last. So this is the web page where you can download the IDEAMAKER software, which we are going to see in the coming slides. So in the web page, you can just download IDEAMAKER software. Make sure you have a good amount of RAM so that simulations can be easy for you to be viewed. So the first thing, I'll just go to the interface of the software. So once we start the IdeaMaker software, this is the interface, and you have toolbars here. You can just add a component or a model by clicking on the add button here. So you can see what are all the supported formats which is available for IdeaMaker software. So the supported formats are .3mf, .stl, .obj, object file, .oltp file. So these are the supported formats. So once we design a component in a designing software, we need to convert preferably to a STL file or a OBJ file and save it in the destination folder. So just double click or click and open this XYZ calibration cube. So in this toolbar, you can see the various transformation icons which is available in this toolbar. The first one is add, where we imported the 3D model. You can also use plus symbol or the import models here to import a new model. And the second one is the delete option, where you can just delete the imported 3D model. And the third one is the view option, where you can just view the component in 3D. You can just zoom in and zoom out. You can view the component in three-dimensional manner. So I can also allot the color of the, not the filament, just to see how it looks after 3D printing. So if I'm giving green color, so just click it outside, so you can view it in the different colors. So this is not possible in Cura software. That is the main difference. The user interface between Cura and IdeaMaker is, it makes a huge difference. So this is bit expert option of 3D printing which is available in the market. So it is an open source software. You can just download it from the download link, and you can easily use it. So you can select the extruder, you can select the color. The next thing is you can pan over the entire 3D printer screen. So the next thing is move option, where you can move the component to the desired part. So if you need copies of the same component, you can just click on Control C and Control V, as we do in Word, Microsoft Word. You can just use Control C and Control V to duplicate the files. So you can use Control Z to undo the duplication. And you can also use this icon here in order to duplicate. So you just click on the component, click on duplicate, and you can increase the number of copies. I've given it as 5, so you'll get around 5 other copies. So you can click Control A in order to select all the components. So the total amount of components here is 6. You can move it to the center by clicking on the make center option in the move command. So it has moved to the center. So if the component is placed here, just click on move, make center. So in some cases, the component will be placed higher to the platform. So in such cases, you just click on platform to make the component sit over the printer platform. So you can also click on arrange all models in order to automatically arrange according to the best orientation. So you can do that. You can click on make center to get it right to the center of the 3D printer platform. And in order to change the orientation, so let's move into the basic characteristics on how a 3D printed part should be oriented in the software, or how the strength varies based on the build orientation techniques. So these are the three basic characteristics of 3D printing which improves part strength. So when we see this, there are three characteristics. First one is the large surface area on the platform. The second one is minimal support, and the third one is minimum Z height. So in case of this VLC logo of VLC Media Player logo, when we see this, there are two types of orientation. One is placed in the upright manner and the other one is placed in the horizontal direction. So in this, when you see, this has a larger surface area and the support is very high and it has minimum Z height. But our condition is it should have a minimal support and a large surface area on the platform. But when we see which has a larger surface area on the platform, this orientation has a larger surface area over the platform. Whereas in this case, only a strand of material is in contact with the platform. The rest of the material is just overhanging materials which is supported by support structures. So in this case, this is the best orientation for FDM technology. So if we do it in FDM technology, this is the best orientation where we can get a good amount of part strength as well as less supports is involved. So when we change the technology, if you are not using FDM technology or if you are using a polyjet technique, this orientation is the best one because the strength increases, part strength increases when the Z height is very minimal. So comparing the Z height of this with the total height of the component with the two orientations, this is very less. And this has a good part strength in other techniques. But in FDM technology, due to the aesthetic requirement of the 3D printed product, you need to choose this orientation as the best orientation. So when we go for specimens, like this is a tensile specimen, which is placed over the print bed, there are three orientations. One is the flat orientation, the second one is on edge, and the third one is the upright orientation. And in this, what do you think, which is the best orientation? Obviously, the flat orientation, because it has the larger surface area on the platform. It has no supports actually. It has no supports and it has minimum Z height, comparing the other both orientations. So this has a high Z height, so the part strength will be obviously less. And this has some amount of supports with happening below the neck portion. So the flat orientation is the best orientation for this tensile specimen. So this is the basic characteristics of any 3D printing method. We need to take into account the aesthetic characteristics should be studied, as well as the part strength of the product is also very important. So we need to weigh on our application where we are going to use it. If you are using it for aesthetic purpose, you need to minimize the supports as much as possible. Or if we are intended to get a good part strength, you need to have a larger surface area on the platform and you should have a minimal Z height, so much possible. So it also depends on the technology used. You can vary the technology if you are getting compromised in any of these characteristics. So I'll just import the tensile specimen itself. So this is a dog bone shaped tensile specimen. According to some ASTM standard, I forgot the standard. 165, 19, and 7 is the scale value. You can just click on scale value to look at the X, Y, and Z dimensions. So you can also change the dimensions here. You can also convert to 200 length, and it will be uniformly scaling in all the axes. Or in case you need to just increase the Z height, just click on deselect the uniform scaling option. And if you want to change from 7 to 10, just input 10. The thickness of the component, gets increased. So it's easily done. So this is the use of scale option, and this rotate option is used in order to place the best orientation. And as we saw in the slide, there are three orientations for tensile testing method. So this is the current orientation is the best technique where the part strength is very high. And the second thing is you can use this orientation as well, where you can see support structures. These yellow colored structures are called support structures, which supports the neck portion or the overhang of the part structure. And in this case, the part strength will be less than the previous orientation. And the next orientation is the upright orientation, where the part strength will be very less because of the very high height of the 3D printed part. So it will have more number of layers when compared to the first orientation. So the number of layers involved in 3D printing part should be very less in order to get a good part strength when comparatively to the other axis. So Z axis should have a lower number of layers when compared to X and Y axis. So just click on reset to get to the first orientation. Then comes the free cut option. This free cut option is used to cut the 3D printed, the design, where you can change the plane. You can just cut the design into two. I'll just show you. So see, you can easily cut or divide the 3D model into two halves or four halves, or according to your requirement. But the cutting plane is a straight one. You cannot free cut, like you cannot cut it in a freeform designing. So you can use Control Z to go back to the previous thing. Next thing is the max fit, which is used to scale the component to the maximum of the build volume. So you can ask me how to interface with the 3D printer which you are using individually. So it's very easy. Just go on to the printer option in the toolbar here. So just click on printer option and go to this is for you can just click on printer settings, and you'll get a pre-defined printers available here, and you can just add or duplicate any printer. So I would like to add a new third-party printer. So you can name it as something Kerala Blasters. So the printer name is Kerala Blasters, and the nozzle diameter of the printer can be defined here, which is 0.4 mm, and the total size of the printer can also be mentioned here. I'll give it as 220 X, Y, and Z axis, 220, 220. So whether the 3D printer has a heated bed facility, you can just click, and it has fan speed control. Just click on, just tick it. And few printers, even though it has 220 XY direction, the actual printer will have only around 218 or 219 mm in actual manner. So in that cases, to eliminate those errors, you can just reduce 2.5 mm from the outer contours of each width, depth, and height. I'm just giving an offset of 2.5 mm so that a good clearance is being given. So the firmware used is Marlin, and there is only one extruder which is used. And these are the general things which is given here. Just add the printer. Okay, you have this, just click on save. So now when we go to the current type of printer, I can select from the list Kerala Blasters. So this 3D printer can be connected with your current third-party 3D printer so that you can start using this IDEAMAKER software for your purpose. So next thing, we are going into the parameters available. So for that case, we will just go across the number of parameters that is available, its explanation and the different classification inside each parameter. So once you input a 3D model using the add command or input model icon, you're inputting the 3D STL file, importing the STL file into the 3D printing software, slicing software, and click on the start button to slice the model. You'll have a start button or start slicing icon placed in the middle of the screen, and you can just click on the button in order to get many options or the process parameters involved. So you can select the printer, you can select the type of filament which is used. So this will be the window which will be available after clicking on start slicing. So I'll just show you how to do that. This is the 3D printing interface. We have oriented the 3D printing component and click on start slicing. So there are no templates available, so we can just click on create. I'll just go with some template. This is our template. So we'll go PLA material. So just give a template name. So you'll get the process parameters which can be viewed here. So layer, extruder, infill, which I mentioned in the previous slide, all the process parameters are available in this window. So we are going to learn about the process parameters now. So as we saw this window there, by clicking on the start slicing, you will get this template window where you can just vary the infill density and number of shells, platform addition, and support. So there is an advanced option where you can change the other parameters as well. So the first parameter which we are going to see is the layer height or the layer thickness. It is also called resolution, and it is defined like it is the thickness of every single layer being laid onto the 3D printing build plate. So if we specify the number of layers as 0.3, so for a 3 mm height 3D file, you will get number of layers is 10. So for a 3 mm thick plate, you will get, if you are specifying the layer height as 0.3, you will get 10 layers within that 3 mm. So if you are going for a layer height of 0.2 mm, the number of layers in the same 3 mm will be 15. And if you are going for a layer height of 0.1, the number of layers involved is 30. So as you reduce the layer height or increase the resolution, the number of layers involved increases. So this layer height is denoted in mm or microns. So 0.3 can be told as 300 microns, 0.2 as 200 microns, 0.1 as 100 microns. So this layer height also depends on the nozzle's diameter. So this nozzle diameter can be changed, which will be explained in the later slides. So this layer height also depends on the nozzle diameter. For example, we are using a 0.4 mm nozzle diameter. So you can almost get 80% of the nozzle diameter as the layer height. So for a 0.4 nozzle diameter, you can achieve up to 0.3 of layer height. You can also achieve 0.2 or 0.15 from a 0.4 nozzle diameter. So the dependent factors are like layer height, layer adhesion, nozzle diameter, and build time or volume is interdependent. Where when we change the layer height, the layer adhesion can increase or decrease. For example, when we see in a 0.3 layer height, the number of layers is 10. And whereas in layer height of 0.1, the number of layers is 30. What do you think, which will have a good part strength? So in case of 0.3 you will get a lesser layer adhesion. Between layers, there will be less adhesion when compared to the layer height of 0.1 because the number of layers involved here is very high. So you'll get a proper layer adhesion when we increase the resolution or decrease the layer height. And it all depends on the nozzle diameter. So if we need a 50 micron layer height or 0.05 layer height, you need to use a 0.1 or 0.2 nozzle so that you can easily achieve the layer height of 50 microns. So by changing the nozzle diameter, you can change the layer height of thickness.
Sorry to interrupt.
Yes,
when
yes,
you
sir.
reduce the nozzle diameter,
Yeah.
what is the chance of clogging or blocking
Yeah.
the nozzle?
Yeah, the chances of clogging is very high in case of reduced nozzle diameters. When we are when we go below 0.2 there are very high chance of clogged nozzles. So you can eliminate by keeping a cleaning part or a cleaning sponge at the start of the 3D printing filament input. So this cleaning sponge will just remove the dirt from the filament surface so that the clogging can be eliminated. So the problem of clogging can be eliminated through that way, and regular maintenance of machine is needed in order to get a lower nozzle diameter. Yeah. Hope it's fine, sir.
Thank you, sir. Thank you.
Yeah. So so as I said, by changing the nozzle diameter, you can also change the layer height proportionately. And when we come to the build time or build volume, as you know, each in a 0.3 layer height, the number of layers is 10. So which say it will take around 3 minutes to complete 10 layers. Whereas if we go for a 0.1 layer height, the number of layers is 30. It will almost take around 9 or 10 minutes to complete the total product. So the time can increase when we reduce the layer thickness. So this should also be taken into account. So if we have any particular demand with the build time or the process constraint or any other customer requirement, if we have less time, you need to go with the higher layer height or lower resolution in order to get the prototype done in a few hours. So this is the first thing which we see when we go inside the advanced 3D printing option. So first thing is the layer, and inside layer you can change the layer height. This is the option where we can change the layer height as per the nozzle diameter or as per the application or the client. So you can input values of up to 80% of the nozzle diameter. So if you are using 0.4 nozzle, you can reach up to 0.31 or 32 of layer height. And if you are using 0.5 nozzle, you can reach up to 0.4 of layer height. So this thing is the first thing, which is the process parameter. And the second thing is the shells. You can increase the number of shells so as to increase the thickness of the model's wall. So this is a 3D printing component, 3D printed component, which represents the different types of variation in shells. So the shell is the outer parameter of each layer, outer perimeter of each layer. So in this case, only 2 shells are being used in the perimeter, and in this case 5 shells are used. In this case the 10 shells are used. In this case 15 shells are used. This increases the part strength as well. So when comparing the 2 shells and 15 shells, obviously 15 shell will have a higher part strength, and even the shell overlap can be inputted. Like you can see maximum shell overlap percentage. So between 2 shells, you can just the 3D printer overlaps one into the other of about 50%, so as to increase the shell bonding. So this is the shells variation. I can show it in the 3D printing software. So I'm just going to start slicing. So I'm giving the infill density. I'll show you. So the number of shells is 2. I'll give 4 shells. You can also change it here. The layer height is 0.2 mm. I'll just put it as 0.3. And the number of shells is 4. And the maximum shell overlap percentage is 50%. So we can just save it and slice it. So the slicing is done. You can get the estimated print time and the estimated amount of material being used and the length of material used. You can also change the estimated price as well, and just click on preview. So you can see 4 shells, 1, 2, 3, 4. Here also 1, 2, 3, 4. So the brown one is the outer shell and the green one is the inner shell. So for each layer, there will be 4 shells in the outer perimeter. So this is how the shell number of shells variation can be done.
Sir, can you
Yes,
show
sir.
the overlap also? Shell overlap also?
The simulation doesn't show the overlap percentage. So in reality, you can if you put it in a 3D printer, there will be shell overlap. So in simulation, there will be no overlap. So because it's an open source software, the overlap is very less. In case of infill, there will be little overlap onto the shells, but between shells, the overlap is not being shown in the simulation. You can also view each layer's lane, like the first layer. First, the shells are being laid, and then the infill starts. So this is the first layer. So in this case, the infill overlap over the shells is being shown, but between shells, the overlap is not being shown in the simulation. But in reality, when we give it to a 3D printer, there will be shell overlapping which is taking place. So the next one is the infill. As we said, the infill is the amount of material involved inside the model. And the more the infill, the more the solid will be. And the part strength also increases by increasing the infill density. So you can vary the infill speed, you can vary the infill overlap, which is the overlap between the infill and the shell. The infill flow rate can be adjusted, and as well as the infill pattern type can also be selected from different patterns. So as you go to the infill characteristic, you can see the infill pattern type. You can just vary the infill pattern types. So there are different infill type. Just a sec. Either mouse. Mouse Yeah. So you can just vary the infill pattern types from the drop-down list available in the window. You can change the infill density here. You can change the infill overlap with the shells here. You can change the infill flow rate here. I'll just show you how it differs. Start slicing. You're going into the template and click on advanced and go to infill, where we have mentioned the infill density is 25. I'll give it as 15. And the infill overlap is 15%, which is very high, which is enough for a 3D printed component to be strong. And we can also increase the overlap percentage. I'm giving it as 50. So if you increase the infill overlap, there is a chance of impressions outside the 3D printed component. So as the shells and infill gets overlapped, so that you can see a projection or an uneven surface over the 3D printed surface. You can change the infill flow rate if needed. You can also change the infill pattern types. There are different patterns available. So if we change the infill density, this is how a 10% infill looks like. This is how a 50% infill looks like, 70% infill and 100% fill density. So these are the different patterns which is available, which we can change in every 3D printed component. You can choose grid, rectilinear, honeycomb, triangle, cubic, concentric, gyroid lines. So when we compare these infill pattern types, honeycomb and gyroid has higher part strength when compared with the other infill pattern types. So I'll just show you the gyroid type. So you can also change the infill angle by providing the angle here, which is also called the raster angle. So just if I click on grid, you can just change the angle 090 or 45 135 or 90 180, which anything can be inputted in the infill angle. So we'll just go with gyroid, which doesn't have an infill angle. We'll just save slides. Going for a preview. So you can see the gyroid type infill pattern. And I guess the infill percentage is not being shown very much here. Overlap percentage is not being shown here in the simulation. So, but in reality, when we deal with the 3D printer, the changes made here gets an there is an effect in the 3D printing process. So, since it's a free software, you'll get to know only few simulations, the infill type, or how barely the 3D printed component looks like. But you can very well change the parameters. So 15 is a decent overlap percentage, and I will give honeycomb pattern type. You can also change the infill angle here. So clicking on preview. So this is a honeycomb infill pattern. So for a honeycomb and gyroid, the amount of time taken is 43 minutes, 11.7 grams. Let's try grid type. So we are trying grid type. I'm changing it as 0 and 90. Go for a preview, and you have seen a 3-minute reduction in the total time taken, and less amount of filament is being used when compared with the other two infill patterns. So there will be a reduction in time when we change the infill pattern as well. So see, this is how a 0 degree and 90 degree infill grid pattern will look like. In case I am giving 45, 135, the grid lines will be in a 45 degree angle. So each of this has its own effect when after 3D printing. The part strength can vary on different infill patterns, and even the angle given to infill can also have an effect on part strength, which can be studied in detail for different processes. So as we saw, this is the layer thickness, where each layer embeds onto the other layer before layer, so that there is good layer addition. So if we have a high resolution part, the layer addition will be very high, and this thing is the number of shells, or uh, uh, you can vary the number of shells, and you can vary the infill, or it is also called raster. So you can just change the raster angle or the infill angle, and in certain higher end softwares, you can also vary the air gap between the infill patterns. So that is also possible, or you can say the varying the infill pattern can vary the air gap percentage as well. Air gap is nothing but the difference between two infill lines. So we have seen the main components of a 3D printing component, the main parameters of a 3D printed component. So first one is the shell, the second one is the infill. Under shells, you can vary the number of shells, or you can vary the layer height, and under infill, you can change the infill pattern, infill angle, infill flow rate. Even you can change the infill density. So depending on the application which we are using, you can choose over the uh, types of different parameters in infill or shells. So the next one is the platform adhesion. So as we see, certain components or certain 3D printed components, when being printed, um, we can face failures in such cases, because the surface area will be very less, which is in contact with the 3D printed platform. So I'll show you. So when we are printing this specimen in this direction, not this specimen, any kind of slim or which has lower surface area in contact with the 3D printing platform, you need to add some material below the lower surface, so that this doesn't topple off during the 3D printing process. So this can be done using the platform adhesion. So I'll go to the simple mode. There is one called platform adhesion. There are three types of platform adhesion. One is the skirt, brim, and raft, and the combination of raft with skirt, and the combination of raft with brim. So when we go to skirt is the amount of material which is being laid offset through the 3D printed part. So when we start 3D printing, the filament will not be fully inserted into the 3D printing head. There may be an air gap present in the nozzle, inside the nozzle. So we need to vary the skirt arrangement. So when we go to platform adhesions, and if we click on skirt only, you can just select the number of loop lines which needs to be printed before going to the 3D printed part. I'm just giving it as 3, and the skirt offset distance is 3. I'll just give it as 10 mm. So you can change, you can see the variation of skirt. So click on preview. So you can see a purple thing which is being printed first. I can show you the simulation. So this is the first layer. And once the printer starts, it lays the skirt. 1, 2, 3. And then the shells are being laid and the bottom layer is being done. And similarly, it starts 3D printing. So this is called skirt, which checks with the 3D printer that the amount of material to be extruded is available, or it shows us that excess of material is being wasted prior to the 3D printing process, so that the first layer is being laid perfectly. You can also change from skirt to raft. The raft is the exact purpose, exact option which serves this purpose, serves this orientation. Just click on preview, and you can see the yellow brown structure, brownish yellow structure placed below the 3D printed part. So this is called the raft. So this is done in order to have a good adhesion onto the 3D printed bed. So once the raft is being laid, then the 3D printed part comes up. So in the middle of the 3D print, it doesn't topple away from the 3D printed bed. So this is the raft option. So I'll tell you the explanation. The skirt is a loop of plastic extruded around the first layer of the model to ensure a steady flow for the model. The raft is composed by a few layers placed on printing surface before the model is being printed to help a model stick to the printing surface. So only in cases it has a low XY dimension, you need to go for a raft. For every 3D printed component, you need not give the raft option, but you need to give the skirt option for every 3D printing process, so as to confirm that enough material is there to start the process. So the last one is the brim only option. You can also change the brim options here, and brim loop lines can be adjusted here. So this can also be used in 3D printing. So you can see it doesn't go inside underneath the 3D printed component. It just supports the first layer, where it holds the layer onto the surface. So there are 5 loop lines, and the one supports the other. So the probability to fall off the 3D print is very less in this case. And I've told about warping effect in FDM 3D printed components. So you can also reduce the warping effect to some extent using this brim option. So these are the raft, skirt, and brim option. So next comes the print and bed temperature. So there is an option for changing the temperature as well. So when we go into the options, just click on temperature, where we can change the bed temperature as well as the extruder temperature. So different materials has different print temperatures. If you are using PLA material, you can set the temperature as 200 to 210 degrees Celsius, and the bed temperature can be 0 in case of PLA. And if we are printing ABS structures, you can use 240 as the print temperature, and you can change the bed temperature as 90 in case of ABS, printing an ABS material. So this can be done, this can be controlled in this temperature tab. So in temperature, there are two kinds of effects that can happen. So one is the under extrusion and the other one is the over extrusion. So under extrusion is a case where the intended print temperature has not been reached yet, because if PLA prints in 200 degrees Celsius and we have given only 180 degrees Celsius to the 3D printer cartridge, it can result in under extrusion, where the extrusion doesn't take place in an even form, and less amount of material is coming out of the 3D printer nozzle. And when we go for a higher temperature, like 230 for a PLA filament, the over extrusion can happen, where the filament, the intended filament maximizes its output and it starts to boil inside the nozzle, and excess of filament is being it will come out of the 3D printer nozzle. So the surface finish can also get ruined in case of over extrusion, and in under extrusion there will be more amount of gaps which is visible in the 3D print, and you will get the optimal extrusion by checking the exact 3D printing temperature for the material. So optimal extrusion, in optimal extrusion you will get the perfect aligning of layers, and there will be no gaps or over extrusion of material. So each and every manufacturer of filament will suggest a temperature which is a workable temperature, and beyond the range of the workable temperature, these two things can happen. One is the under extrusion and the over extrusion. So these are the different types of materials and the glass transition temperatures of the particular material. So if you're going for PLA material, the glass transition is something around 60 to 70 degrees. So in 70 degrees, deformation can start happening. So if you go for an altum material, the glass transition is very high, and in nylon, it's comparatively, it's in the logarithmic scale. Like the least is the PLA and the higher one is the altum material. So in between, the ABS, PETG, nylon, polycarbonate stands. So these are the temperature levels for different 3D printing materials. For PLA, the print temperature can be placed 205 plus or minus 10 degrees Celsius. This is the temperature of, mentioned by the Filamentive brand. So you can, they are also telling the bed temperature to be set at less than or equal to 60 degrees Celsius. And the print speed can be set to medium or high. Fan speed can be set to medium or high. Whereas when we are using ABS as raw material, the fan speed will be low, or you can set it to 20% or 0%, so that you can get the best finish out of the 3D printer. So each material has its own temperature characteristic, which varies, depends on the manufacturer of the 3D filament. So next thing is the top and bottom layer infill angle. So when a product is being manufactured, as we know, we can vary the infill angle and the infill density, but the top and bottom layers needs to be closed, and the infill should be 100% in such cases in the top and bottom layers. So in such cases, you can give the or vary the solid top and bottom layers, and you can input the amount of layers that is that can be involved in the top layer and the bottom layer. I can show you in the preview itself. So solid fill, I'll give it as 5 and 5. So if you see the preview, I'll go to the first layer. 1, 2, 3, 4, 5. After 5 bottom layers, the infill starts. So this is the top and bottom. This is the bottom infill. and we will go to the topmost layer. And here also 1, 2, 3, 4, 5. So 5 top layers and 5 bottom layers is involved in this process. So you can just vary the top and bottom layer infill or the number of layers in the solid fill tab. You can also vary the flow rate, the amount of material that is coming out of the nozzle. You can also vary the type of pattern. You can change the pattern type of solid and top and bottom layers. And you can also change the angle of the top and bottom layer. Similar to the infill ratios angle, you can change the solid top and bottom layers angle as well. So next one is the printing speed. So this needs to be adjusted based on the material used. And if you are using a normal material like PLA, the printing speeds can be high, even above 100 mm per second based on the stability of the machine. You can reach up to 200 mm per second. So the default printing speed everyone will be using is around 80 mm per second. You can define the printing speed for inner shell, outer shell. First layer, you can define the printing speed, which is preferably very low, so as to stick the first layer onto the 3D printed build plate. You need to lay it in a very low speed, so that you will have a good adhesion between the build plate and the 3D printed component. So even the infill speed can be varied, and the bottom and top infill speed can be varied. XY movement speed can be varied. Z-axis movement speed can be varied. Support speed can be varied, which all depends on the type of material used. If you are going for polycarbonate or nylon 3D printing filament, you can just vary the speeds. You need to set it at a lower speed in order to get a good finish. So the next thing is the nozzle diameter. So generally, every 3D printer uses 1.75 mm as the filament filament diameter. So there are also 3 mm filaments which is available. So generally, all the commercial 3D printers uses 1.75 mm, and these are the different varieties of nozzle or different nozzle diameters that is available in the market, which varies from 0.1. 0.1 is also available. 0.2 to 1 is preferably available in the market, and these are brass nozzles. And you also have hardened steel nozzle, Oslo ruby nozzle, which these things can be used if you are printing carbon fiber along with PLA or ABS filament. So the wear and tear of the nozzle will be very less in such cases. So if you are using a brass nozzle for carbon fiber filaments, the wear of the nozzle wear rate will be very high. So when we compare the different nozzles, if you're using a 0.6 nozzle, in the same 3 hours, see the size of the component that can be printed. So if you are using a higher nozzle diameter, you can swiftly produce components. And if you're using a lower nozzle diameter, the process is a bit slow. And when you're going for a lower nozzle diameter, the print speed also gets minimum, and so the printing time will be higher in such cases. So this is an optimization fishbone diagram where you can vary the different process parameters in order to study the surface roughness, dimensional accuracy, build time, tensile strength, compressive strength, flexural strength. This I've taken it from a journal. So you can just click on the optimization process parameters. You can just Google it in order to view the fishbone diagram of the process. So you can just vary the layer thickness, build orientation, print speed, raster width, which is the infill width, and extrusion temperature to study the surface roughness, and similarly these parameters to study the dimensional accuracy. So as we saw, just click on start slicing, and going in you can just vary the required 3D printing process parameters. I'll give it as 2 shells. The maximum overlap percentage is 50. 0.3 is the first layer height, and there are other advanced options as well. You can just click on this print external shells first, print infill first, if we need to change the order of shells and infill being 3D printed. So one more option which is used is spiral base mode. If we click this, let's see how the 3D printed component looks like. See the amount of time taken. It finishes in 29 minutes. You can view the preview. So this is how a base mode looks like. So the the upper top portion will be open, and there will be no infill being generated in the model. So if you need to do flower bases or similar models, or just to see the aesthetic or aesthetic view of the component, you can just click on base mode in order to swiftly 3D print the part. So you can change the nozzle diameter here. You can change the infill density, infill overlap. You can change the infill pattern type. You can change the top and bottom layers. You can change the type of the pattern. Supports can be changed, and the supports infill ratio, the supports pillar size can also be varied here. Platform additions can be added. So I'll be using only skirt for this 3D printed component. And you can also vary the fan speed here. Generally, the first layer will have 0 fan speed, so as to nicely adhere to the 3D printed build plate. And from the second layer, the fan speed will be, you can vary the fan speed as per the printing filament which is being used. If you're using a PLA filament, you can just put 100, or if you're using a ABS filament, you can change to 20. Right now, let's think we are using PLA filament. So the temperature can be varied. I'll put it as 210. I don't need a heated bed temperature because our normal temperature will be around 30 degrees or 28 degrees room temperature. So I'll put it as 0 degree. You can also change the speed, the general speed, printing speed to the first layer speed, XY speed and Z speed. Everything can be changed. Even the support speed can be changed. There are few advanced options which speaks about the acceleration and jerk. So once the print, if you need to accelerate more than the 3D printer's intended speed, which is given here, you can just click. You can click on acceleration and change the per second squared speed here. And jerk is the it allows the extruder to change axis during 3D printing. So it is how a velocity gets changed from one to another. So this jerk can also, these are all advanced options which is available, which is normally not required to try it out. And even a few filament flow rate settings can also be changed. If some anomaly is happening, like if we have a nozzle which is weird out and it has become 0.4 to 0.5 mm, you can just decrease the filament flow rate so as to decrease the amount of material coming out of the 3D printing nozzle. So the flow rate can be varied in this. So you can just override the filament settings as well. And there are a few other techniques as well. You can just you need to concentrate more on the layer, infill, solid fill, support, temperature, speed. These are the important parameters which needs to be changed. And if you need to change color of the component after certain printing, after certain height, so as we see, the total height of the component is 7 mm, and we need to change the color of the component. So we'll just give start slicing and go to other, faucet height, and give 3.8. So after finishing the 3.5 mm layer, the nozzle stops printing and moves away from the 3D printing component. Just add this point. So after 3.5 mm, before starting the 3.8 layer, the nozzle moves away so that you can change the filament color and input another color onto the extrusion head. So you can just delete it if needed. So the last one is the G codes. These are the start and end G code, which is mostly same for all the 3D printers commercially available. So you can change if required. For any 3D printers, first the extrusion head goes to the home position and then it starts 3D printing. So these movements are being depicted here. The G28 represents the motion of the X and Y and Z axis. So first the G28 X0 Y0. First the X and Y axis goes to the home position, that is the 0, and Z goes to the 0. Then some filament, then the total setup moves to the Z15 position. Like if the printer head is placed at the home position, it goes to the printed bed goes decreases 15 mm at a feed rate of 300. So these are certain G codes available in the start and ending of the process. So once we slides, I'll remove the spiral waste mode. Save slides. You can see the estimated print time. As I said, you can see the amount of material used. You can see the amount of length of material used and the price as well. So in certain cases, if you have a Wi-Fi connection, you can directly upload it to the printer. Or also there is a setup called Octoprint, which is a separate Wi-Fi module or slicing setup where you can directly upload to the Octoprint cloud data. You can also export this thing as G code onto the pen drive or SD card. I'm just exporting the tensile G code file. It will be exported as G code to desktop. So by exporting this, sorry, I'll just open with Notepad. This is the G code of the tensile component which we are doing. You can see the start code here. This is the start code here, G28X0Y0Z0, and it starts printing, and the printing starts, and it has so much of layers. See the depth of the G code, and this is the final end code. You can get to know the print time, material used, and everything can be decoded from the G code as well. So once the G code is being generated out of the slicing software, then you can directly input the G code into the 3D printer, and clicking on the G code, the 3D printer starts manufacturing the component. So that is how a 3D printing slicing software works, and these are the basic parameters that is involved in a 3D printing process. Certain researchers are being carried out right now. So few composite 3D printing materials are being compared, preferably ABS carbon fiber, PLA carbon fiber with PETG. These things are being manufactured out of the 3D printer by changing the process parameters and are being compared. Even there are comparison of post-process materials. Like after 3D printing a component, you can use various other methods to enhance the finish of the FDM printed component. So I can use salt method, acetone vapor treated method, epoxy coating method to increase the surface finish of the components. And after increasing the surface finish, you can compare the mechanical characteristics and other chemical characteristics of the 3D printed component. You can just search for salt method. This is a method where the 3D printed component is kept or immersed inside powder salt. The powder salt should be very fine so as to increase the finish of the 3D printed component. After immersing the 3D printed component into the salt, it is placed in a furnace. It is melted above the melting point, like around, if we are using PLA printed component, we will be melting around 220 degrees Celsius for around 10 minutes of keeping it in the furnace. Then we will take it out, and the melted part starts regaining the shape, and the whole component will look as a single component. I can show you the video. So this is a PETG FDM process printed. See, after processing, the surface finish of the component. So I'll just fast forward it. This is a 3D printed component directly taken out from the 3D printer. And this thing is printed in 100% infill. Then they are placing the powder salt into a beaker or a container, and they are placing the 3D printed component into the powder salt, and they ram it to pack the powder salt well and keeping it in a oven. So they are heating PLA around 230 and 245 degrees respectively, and after 45 minutes of baking, they are just taking it out, and after, just see the surface finish of the component. You can also use these types of post-processing methods in order to compare the part strength in such cases. So hope you had a good session on different process parameters used in 3D printing software or 3D printer. And this is our mail ID, and this is our Instagram ID. You can also just search for Insta3D Technologies Coimbatore, and this is my contact number. You can contact me for any queries on 3D printing technology. So this is our website. You can just go in, and you can also review us in Google. Just search for Insta3D Technologies Coimbatore. Any questions? Thank you, Prathamesh. Muhammad Mustafa has raised his hand. Any doubts? Yeah, I have a message. How to communicate 3D printing software with MATLAB interface? I'm not very much familiar with MATLAB. I would try to answer the question later, maybe later. Any other questions?
I think participants can ask further questions if you have any further clarification required. So they're asking on the MATLAB interface, I think.
Yes, sir. I'm not very familiar with the MATLAB interface. Yeah, that's the issue. Yeah. Maybe I can answer them later. I'll just note down his name.
So any further questions, you can unmute and you can directly ask the resource person so that he will be answering your queries.
All from
Sir,
Kerala. Yeah. Sorry.
sir, have you gone to metal 3D printing? Your company is doing some work on that.
Yes, sir. We are outsourcing the metal 3D printing works. We have tie-ups with other companies where we can metal 3D print.
So what are the training programs you are providing to institutes and all? What are
certain value-added courses are being conducted in certain institutions. It's like they will have a 1 week value-added training session for every semester. So it's like one credit point or something. So we have a set of syllabus where we teach them the introduction of additive manufacturing technology, technologies available, design based on 3D printing technique, the slicing software, the design software, part of design software is getting involved in the course, as well as we'll have a live demonstration on the 3D printer as well.
Okay.
Even we can also teach students how to develop 3D printers.
That is a hardware.
Yeah, hardware components, and software parts. Certain things can be taught to them.
Okay.
Thank you, Nidhi.
So I think there is no more queries from the participant side. So I invite our faculty Jiffin to put the vote of thanks for the sessions.
Thank you, Joseph, sir, for taking this wonderful session on this IDEAMAKER software. So this FTP session was very informative and helped to learn different aspects on 3D printing. So once again, thanks, Joseph, sir, for this session, for sharing your experience on different aspects of the 3D printing software, especially on IDEAMAKER software. Thank you.
Thank you, sir.
We hope to contact you in future also, sir. We have our labs are also getting ready to train the students, so we'll be contacting you in the future.
Sure, sir.
Yeah,
Always
work with you in future. Yeah.
Okay, sir. Great knowing you all.
Sure.
Thank you.
Thank you very much.
Thank you, sir. Thank you all. Have a nice day.